We are continuing our discussion on iterated integrals. We have a nice theorem. Fubini's theorem says if f is continuous on rectangular region that is defined as R equals to the sets of ordered pairs x and y, such x is bounded between two vertical lines, A and B, y is bounded between two horizontal lines, C and D, or visually, if you have a rectangular base down here, the double integral of function f of x and y is nothing but you can find the definite integral of the function with respect to y first, then take the integral with respect to x, or you can take the integral with respect to x first, then take the integral with respect to y. Just be careful about the boundaries here. In this case, the inner integral is with respect to y, and as you can see, y is bounded between c and d. So that's how you have c and d. But in this case, if you're taking the inner integral with respect to x, the boundary for x is between a and b, as you can see just right here. So be careful about these two important bounds for x and y when you're switching between x and y. More generally, this is true if we assume that f is bounded on R, f is discontinuous only on a finite numbers of smooth curves, and the iterated integrals exist. Let's take a look at a couple of examples for you. Remember from elementary calculus, the integral, the definite integral of dx is x, ranges between a to b, which is b minus a. In this example, I ask you to calculate the iterated integral of 1 dy dx. So basically, the inner integral is with respect to y. You can group these to make it a little bit easier to visualize. So your inner integral is the integral of 1 dy, y bounded between -3 and 8, and then you take the outer integral with respect to x. But the integral of 1 dy is y, and y bounded between -3 to 8. Then you take the outer integral with respect to x. Y bounded between -3 to 8 is 8 minus -3, which is 11. Then you take the outer integral with respect to x, which is 11x, x bounded between 4 to 9. So you have 99 minus 44, which is 55. In the next example, we have the iterated integral of x squared sine y dy dx. So as you can see, the inner integral is with respect to y, and y is bounded between 0 to pi. The integral of sine y is negative cosine y, and y is bounded between 0 to pi. Then you take the outer integral of x squared with respect to x. This is equal to, well, if we calculate negative cosine y, y bounded between 0 to pi, we have negative cosine pi plus cosine of 0. Then you take the integral with respect to dx of x squared. This is equal to, well, here you have 1 plus 1, because you have cosine of pi, which is -1. Negative times negative is 1, plus cosine of 0, which is 1, and the definite integral of x squared dx. So we end up with the definite integral of 2x squared dx, x bounded between -1 and 1. And remember the formula from our elementary calculus. If you have a power function, the integral is u to n plus 1 divided by n plus 1. So since n is equal to 2, you get 2/3 x to the third, and x bounded between -1 to 1. In turns, it is 2/3 1 to the third minus negative 1 to the third, which is basically 4 over 3. What if we switch these around? Suppose I ask you to calculate the double integral of x squared sine y. Now I have dx dy. Please note that now my x is bounded between 0 to pi. So as I mentioned before, when you're applying Fubini's theorem, be careful about the boundary for x and y. This can be written as the definite integral of x squared dx. X is bounded between 0 and pi. Then you can take the integral of sine y with respect to y. The definite integral of x squared dx, x is bounded between 0 and pi. As you remember, using the power rule, it is x to the third divided by 3, and x is bounded between 0 to pi. Then we take the outer integral with respect to y. If you plug in pi, you get pi to the third divided by 3, and 0 make this term to vanish, so we don't need it. Then you take the integral, the definite integral of sine y dy, and y bounded between negative 1 and 1. Remember the integral of sine u du, which is negative cosine u plus c, and since you have definite integral, you just end up with negative cosine y. So we copy down pi to the third divided by 3, and the integral of sine y is negative cosine y. Y is bounded between negative 1 and 1. You just plug in 1, then you plug in negative 1. So you have pi to the third divided by 3 times negative cosine of 1 minus minus, which gives you plus cosine of negative 1, which is equal to 0. So compare these two examples, the previous one and this one. Switching the order is very important. You need to make sure when you're using x, you have the boundary for x, and when you're using y, you have the boundary for y.